everyone, welcome to the third episode of our video series about television remote controls. As promised, in this episode we are going to examine the external structure of the remote control. The section consists of six main parts: the front cover, rubber buttons, battery retaining foam, you can see here, rear cover, battery compartment door, and a single screw that holds all these parts together. So let's start with the front cover. At first glance, this cover may look like nothing more than a simple piece of plastic, but in reality, almost every millimeter of it has been designed for a specific purpose. On the outer surface, in addition to the Philips logo, we can see the names of several buttons such as TV Guide, Lead, Source, and Smart TV. When we turn the cover over, we can see several codes and numbers. Each of them provides information about the material of the part and the manufacturing process. 07 inside the triangle. This is the recycling code used for mixed engineering plastic, classified under the other category. The next one is ABS. This indicates that the cover is made of ABS plastic. ABS is a durable, easily processable, and cost-effective material that is widely used in the production of television remote controls. And finally, HOF underline 471 and 1.1. These are internal factory codes used for part and mold identification, as well as for tracking the manufacturing process. So, why does the front cover exists in the first place? The front cover has three main functions. The first one is to protect the internal components from impact, dust, and direct contact. The next one is to provide visual guidance to the user through labels, symbols, and the appropriate arrangement of the buttons. And finally, to guide and limit the movement of the buttons, preventing them from becoming loose or getting stuck when pressed. So far, we've looked at the labels on the front cover and its main functions. Now, let's examine it from the inside and see what each section was designed to. When we looked at the inner side of the cover, we can see a series of reinforcing and guiding structures, each with specific function. The first one is reinforcing ribs. On the back of the front cover, we can see network of plastic reinforcing ribs. These ribs increase the stiffness and strain of the cover without significantly increasing its weight or the amount of plastic required. They also help prevent the cover from bending or warping when buttons are pressed. The next one is IR window housing. At the very top of the cover, there is a semicircular opening for the infrared transmitter. Together with the rear cover, this section forms the passage for the infrared LED, allowing the infrared beam to travel toward the television without obstructions. And the next part is support columns and support grids, as you can see here. Between different sections of the cover, we can see these plastic bridges. These bridges help prevent the cover from twisting or deforming when the buttons are pressed, while also increasing the structural integrity of the housing. And finally, we have ergonomic curvature. The edges of the cover are fully rounded and have a gentle curvature. This design makes the remote more comfortable to hold and prevents sharp edges from coming into contact with the hand. As we've seen, even the parts that are completely hidden from view have been carefully designed. But there are also several interesting design decisions on the outer surface of the cover. One of them is the position of the Philips logo. Why do you think the logo was placed here instead of at the top? The brand logo is positioned near the bottom of the cover because this is one of the areas that has the least contact with the fingers. As a result, the logo is less likely to wear off over time due to friction and contact or perspiration. But the design of this cover is not limited to structural strength and the positioning of components. The way the labels and button name are displayed is also based on principles of industrial design. You may be wondering, why are the names of some buttons printed on the cover while others have no names at all? So, in industrial design, this is known as visual prioritization. Buttons such as numbers, volume, channel, or OK use widely recognized symbols, so there is no need to write their names separately. However, buttons such as TV Guide or Smart TV or Multiview have more names or have more functions, specific functions. Therefore, their names are printed on the cover to prevent user confusion. This approach not only improves readability but also prevents the appearance of the remote from becoming unnecessarily cluttered. So far, we've examined the front cover and its role in protecting the internal components and guiding the user. But the cover itself cannot do much on its own. The main role belongs to the part we interact with every day. What is that? This is the buttons. The industrial terminology, the complete set of buttons is a remote control is called a conductive rubber keypad or simply a silicone keypad. These buttons are not merely rubber pieces that we press. Together with the carbon peels underneath them, they function as electronic switches. The main purpose of this assembly is to provide the user with a tactile pressing sensation and to establish an electrical connection between the conductive traces and the circuit board through the carbon peels. Now that we understand the overall structure of this keypad, let's take a closer look at the markings and codes molded into it. So, what is this HO707 code molded into the rubber? These types of codes are generally used for tracking the manufacturing process, identifying the mold, and maintaining quality control traceability. However, the exact meaning of these codes can usually only be determined from the manufacturer's internal documentation. But this keypad is more than just a few identification codes. The material used in its construction also play an important role in the performance and durability of the remote. So what are the buttons actually made of? If you open the television remote, you will see that all of the buttons are connected to one another, forming a single interacted sheet. This sheet is made from two fundamentally different materials. Main body of the buttons. This section is made of silicone rubber. Silicone is a flexible, non-toxic, and highly durable polymer. It has excellent resistance to temperature change, moisture, and long-term aging. Compared with many conventional types of rubber, silicone also takes longer to wear out and develop cracks. The next one is button section of the buttons. Directly underneath each button, there is a black color section known as a carbon fill. This part is made by combining silicone rubber with graphite or carbon powder, giving it electrical conductivity. Now that we know what materials make up the keypads, let's turn it over and examine the other side to see what each section is designed to do. When we look at this side of the silicone keypad, we can see that every part has been designed for a specific function. The first part is silicone domes or carbon fills. Each button consists of a flexible silicone dome with a conductive carbon fill at its center. When the button is pressed, the silicone dome transfers the applied force to the carbon fill. The carbon fill then bridges to conductive traces on the circuit board, creating the electrical connection that indicates a button press. This allows the remote control circuit to detect which button has been activated. The next part is alignment pins. As you can see here, The holes in the keypad fit over guide pins on the remote housing and the circuit board. This ensures that the keypad is positioned precisely and that each carbon field lines up with the correct contacts on the circuit board. And the last part is integrated silicone sheet. All of the buttons are manufactured as a silicone piece. This design simplifies assembly, prevents the buttons from shifting or getting lost, and improves the remote resistance to dust and moisture. Now that we became familiar with the different parts of its silicone keypad, an important question comes to mind. Why did designer engineering choose a silicone keypad instead of mechanical switches? There are three main reasons. The first one is a more integrated design with greater resistance to dust and moisture. The next one, a long service life with the ability to withstand millions of button presses. And the last one is lower cost and a simpler manufacturing and assembly process. Of course, understanding the advantage of this design is not enough. Let's take a look at what actually happens inside the remote when we press a button. The operating principle of the remote button is quite simple, but also remarkably clever. It takes place in three stages. The first stage is normal state open circuit. Under normal conditions, the carbon peel does not touch the contacts on the circuit board. The circuit is therefore open, and no current flows between the two conductive traces. The next operation is button press. Closed circuit. When we press the button, the carbon peel moves downward and bridges the two conductive traces on the circuit board. As a result, the circuit is closed and an electrical connection is established. And finally, we have common transmission. The remote microcontroller detects this connection while scanning the key matrix and identifies which buttons has been pressed. It then sends the corresponding command to the television as an infrared signal. Of course, no component has an unlimited service life. Over time, accumulated dirt or wear on the carbon field can cause some buttons to stop working properly. This combination of simplicity, durability, and low cost is exactly why this type of keypad is not limited to television remote controls. Today, the same mechanism is also used in game controllers, calculators, and even some automotive buttons. So far, we've become familiar with the most important part of the remote that we physically interact with, the buttons. But inside this remote, there is another small and often overlooked component. At first glance, it may seem insignificant, yet it plays an important role in keeping the remote working reliably. The small piece of the foam located above the battery compartment is commonly referred to as a battery retaining foam or shock absorbing pad. So why is this small piece placed here? At the first, stabilizing the batteries and preventing momentary power interruptions. AAA batteries can shift slightly as a result of impacts or movement. This foam applies gentle pressure to the batteries, keeping them firmly in place and reducing the possibility of momentary interruptions in the power connection. The next one is preventing battery rattling. Because batteries from different manufacturers can have slight dimensional differences, a small amount of clearance may exist inside the battery compartment. The foam components for these manufacturing tolerances and prevents the batteries from moving and producing rattling noises. The next part is reducing impact and on the battery contacts. When the remote is dropped like that, the mass of the batteries can exert force on the springs and contacts connected to the circuit board. The foam absorbs part of the impact energy, reducing the mechanical stress transferred to these connections. Now that we know what this small component does, let's take a look at what it is made of and how it can perform these functions for years. This compound is typically made from engineering firms such as polyurethane or PU and EVA. These materials have good elastic properties, provide electrical insulation, and offer a suitable resistance to moisture. But choosing the right material is only one part of the design. The way the foam is installed is just as important. If we take a closer look at where this foam is positioned, we can see that it sits inside a small plastic groove. This groove is initially designed to be slightly smaller than the dimensions of this foam. When the foam is inserted, it becomes slightly compressed. The resulting friction force keeps it firmly in place without the need for adhesive. That means there is no need to use glue. This approach not only reduces manufacturing costs and speeds up assembly, but also avoids problems caused by adhesive degradation over time. And at the end of the product's service life, it makes disassembly and recycling of the components easier. So far, we've examined the components that are housed inside the remote casing. Now it's time to move on to the fourth part of the remote's body, the rear cover. The rear cover does more than simply protect the internal components. It also plays an important role in the structural strength of the housing and in keeping the entire assembly securely together. On the inner surface of the rear cover, we can see the same identification code that were present on the front cover, as you can see here. Since we've already explained the meaning of these codes, let's go directly to the structure and functions of the rear cover. The rear cover has four main functions. The first one is to protect the internal components and increase the structural strength of the housing. The next one is to hold and stabilize the circuit board and other components. The next one to form the battery compartment and keep the batteries correctly positioned. And finally, to provide an ergonomic shape that makes the remote comfortable to hold. Now that we understand the main function of the rear cover, let's examine it from the inside and see how each section contributes to this function. If we take a close look at the inner surface of the rear cover, we can see that almost every section has been designed for a specific purpose. Some features, such as the reinforcing ribs, as you can see here, the opening for the infrared transmitter, and the ergonomic curvature, are similar to those found on the front cover. Since we already explained these features in detail when examining the front cover, this time we will focus on the new and different features of the rear cover. The first one is battery components. The central section of the cover forms the compartment for two AAA batteries. The walls of this compartment are shaped to keep the batteries in the correct position and maintain a stable electrical connection between the batteries and the metal contacts inside the battery compartment. The next part is battery foam seat and a spring retainer. At the upper part of the battery compartment, there is a dedicated area for the battery retaining foam and the battery contact spring. At the lower here section, a plastic protrusion and groove hold the outer end of spring in place. This design prevents the spring from shifting when the batteries are replaced or when pressure is applied, keeping it securely in its correct position. The next part is housing locking grooves, right here. Along the edge of the housing, there are grooves and slots that engage with the plastic clips on the front cover. This connection allows the two halves of the housing to snap together without unwanted play. It increases the overall structural strength and also prevents unwanted noise or vibration during use. And finally, we have a screw bus. At the lower section of the cover, we can see a cylindrical support designed to accommodate the screw. The support transfers the force of the screw into the housing and allows the front and rear covers to be securely fastened together. At the same time, it helps prevent the plastic surrounding the screw from cracking or breaking when the screw is tightened. So far, we examine the mechanical structure of the rear cover. But in addition to its mechanical features, this cover also carries several symbols and identification codes that provide important information about the product's standards and identity. The first one is International Standards Marks. The CE mark indicates that the product meets the applicable requirements of the European Union concerning areas such as safety, health, electromagnetic compatibility, and other relevant regulations. The next one is Crossed Out Wheel Bin, VEEE. The symbol known as VEEE indicates that the product should not be disposed of together with household waste. At the end of its service life, the products should be taken to an appropriate collection point for the collection and recycling of the electronic equipment. The black horizontal bar underneath the bin generally indicates that the product was placed on the market after 2005. In addition to these standard markings, several identification codes are also printed on the cover. These codes are used for production, traceability, and product management. So the code starts with HOF. This code is a technical identifier for the remote control. It is used by the manufacturer to identify the model and its compatibility with certain Philips television models. The next one, 160901. This number most likely represents the production date or the date the product left the assembly line using a year-month day format. If this interpretation is correct, it corresponds to September 1st of 2016. The next one is 08197. This number is most likely a serial number, production batch number, or factory traceability code. Codes like these are generally used for quality control and for tracking the product throughout the manufacturing process. Now we come to the fifth component of the remote's external structure, the battery cover. It may look like a simple piece at first glance, but it plays an important role in keeping the batteries in place and completing the structure of the remote. The battery cover also carries the same identification codes found on the plastic body components that we explained earlier. So instead of repeating those codes, let's move directly to the design and functions of these components. The main function of the battery cover are, first, to close the battery compartment and prevent the batteries from coming out. The next one is to apply gentle pressure to the batteries and maintain a stable electrical connection. And finally, to complete the remote's integrated and aesthetically consistent appearance. Here's an interesting detail. The material used for the battery cover is usually the same as the material used for the rear cover. Engineers intentionally do this so that both components have similar rates of thermal expansions and contraction when the temperature changes. As a result, the battery cover maintains a more stable fit and more reliable performance under different temperature conditions. Now that we understand the main function of the battery cover, let's examine it from the inside and see how these functions are actually implemented. So, if we take a close look at the battery cover, we can see that almost every part has a specific function. Upper locking tables. At the very top area of the cover, there are four plastic tabs. When the cover is installed in these tabs, first enter the grooves in the rear cover, guiding the battery cover into the correct position. Then, once the lower locking latch engaged, the cover becomes fully squared. The next part is lower locking latch. At the bottom of the cover, there are two flexible plastic locking latches. These latches form the final locking mechanism of the cover. When the cover is closed, they snap into the corresponding grooves in the rear cover with a characteristic click. This allows the battery cover to remain securely attached to the remote without the need for a screw. And finally, battery pressure reads. On the inner side of the cover, there are two parallel plastic protrusions. When the cover is closed, these protections apply gentle pressure to the AAA batteries. This keeps the batteries securely in place and helps maintain electrical contact between the batteries and the metal contacts, even when the remote is subjected to an impact or movement. So far, we've examined all of the external components of the remote one by one. But there is still one interesting question left. Why does this remote use only one single screw? Most of the housing is held together using plastic clips and snap fit connections. This approach speeds up assembly and reduces manufacturing costs because on the production line, the components can simply be pressed into place and locked together. But then, why wasn't this one screw eliminated as well? Because the lower section of the remote contains the batteries. And this is one of the areas that experience the greatest mechanical force when the batteries are replaced. The signal screw increases the structural strength of this area and helps prevent the housing from accidentally opening or the plastic clips from becoming damaged during long-term use. As you've seen, even the external structure of the television remote is a full of engineering details. From the choice of plastic material and the design of the buttons to the battery retaining foam and the snap fit housing system. Almost every detail has a specific purpose. Of course, there are many more technical details and interesting design decisions hidden in this remote. But to keep the video from becoming unnecessary long, I've tried to select and explain the most important and useful ones. Well, everyone, we've reached the end of this episode. I hope you enjoyed the video and learned something new. If you have any question, comments, or suggestion, be sure to share them with me in the comment section. In the next episode, we'll go inside the heart of this remote and take a closer look at its electronic circuit board. Until the next video, goodbye!